Let's say I want to minimize ax minus b. Okay, this is what we talked about like last time. Okay, 2 norm square, and there's a half. Okay, so if you forgot how to derive the slope, go back to what we did last week. Okay, so the gradient of this thing, and if I call this f, okay, I call this f. The gradient of f, that means the partial derivative of x1, x2, x3 up to xn will be a transpose a x a transpose b. Again, if you forgot what it is, how this is derived, go back to the material for the last week. Then what's next? What's gradient descent? Gradient descent is, this is a new one, so I write a plus sign here to mean this is new. It's what? It's the O1 minus a step size. Let me call this alpha, and then gradient. Okay. So let me write something like this. So from this expression, we know that what is this gradient. Then now we need to find this new point by just translating this thing in MATLAB. So let's say I have A. So usually you have the size of the matrix, right? M by n. Okay, m by n. Let's say, okay, just say m is make it simple, 5 and n is 6. Okay, and then A, I can have some matrix, right? Now because we are just try for fun, I will make A a random matrix. So if I run this, this is my A, and I also need B, right? B will be, again, I make a random matrix. It will be m by 1. Okay, m by 1. So now I make a B. Okay, this is my B. Now I will make my X. Our point is to know what is the X. So I will need to have an initial guess. So I call it XINI. INI means initial. Then what? I make a random vector. Okay, again, n by 1. Okay, so now I make a random vector. So is XINI the minimizer of this thing? Well, how do we know? We compute this thing. So what is this thing? AX minus B, right? Then we can compute what? Compute the cost value at XINI. And how do we compute? Well, just there's a half, right? Half means 0.5. Okay, I just have 0.5. And then times what? This thing, this is a vector norm. So I can say norm, this is calling MATLAB function, A times XINI minus B. And then that's it. But there's a square here. So I need to type the square here. So if I run this, it will give me some number. So this is saying that if this is my XINI, then AX minus B for X equal XINI in this expression will be 22 something. Okay, this is like calling a function norm. That means it's doing this. Or you can say, well, I know what is the vector norm. It's AX minus B transpose multiply itself. Then I can also do this. So 0.5 times what? Inner product between this and itself, right? So this is a vector. So I take a bracket, have this, and then I have also the bracket term, and I know that it is the transpose, the first guy multiply the second guy, right? So I can do this. You see, this number and this number are same number. So this is simple, right? Now I don't want to show them, so I hide them. Okay. Then what's next? We are going to run what? Gradient descent. This line. So basically, this will be something like what? X equal to x minus alpha times grad f. Okay, I type this. Now, if I run this, it will be error. Why? Because if I run this, first of all, I have never defined what is x, and also I have never defined what is alpha. I also have never defined what is grad f. Of course, it will be error. But since MATLAB read from the left to the right, so when it see this one is okay, but it will not know what the heck is this x. And if you look at the workspace, there's no x. So of course, this is error. Okay. So what we are going to do, we will say x is my XINI. That means what? X is my starting point. Let me clean this. So I will have x now. So now I have x. But if I run this, there will be error. Why? Because there's no alpha. So for simplicity, let's say alpha is 1. Okay. Let's say alpha is 1. Now I run this, clean this first. There will be error. There's no grad f. So I need grad f. Okay. Grad f. So what is grad f? Looking at this expression, A transpose AX minus A transpose B. Then I do the same thing. A transpose multiply A, right? A transpose multiply A is this thing. Multiply X minus A transpose B. Okay. Minus A transpose times B. Okay. Now I run this, there will be grad f. You see, number. Okay. Now if I run this thing, it should be correct. Now you see, I have a new point that is like this. Is this value better than the previous one? Let's see. So the previous norm value is something like this. Let me run this. The previous norm is 22 point something. That means the initial x give you this number. Now if I replace this XINI by x, okay, now you see this number explode to, wow, a very big number. So that means what? Function value not decreasing but increasing. Well, that means what? probably the step size is too big. Let me clean this up. So first I let x is xi9. Now let's say I make alpha 0.001. Okay. So now I make this, and now I compute the grad f again, and now I have this update, and now I have my, this is what my old value 22 something. Now this is my new value. Okay, now you see 22 go down to 21. So that means what? In this case, my function value go down, and that means this alpha is a correct alpha. Why this is the case? We have a function that probably looks something like this. So for this function, previously I said alpha is 1. Maybe for this function, when alpha is 1, is something like going to here. So this is like 1. So if I move along this direction with a value 1, it goes up. Now I make it 0.001. So let's say very small. So it's like moving in this, okay, about 10 times less. Okay, the figure is not in scale, but you got the idea. So now I'm, instead of moving this big, I move this big. So now it go down. Okay, but now it's not going down too much. Maybe I can use a better number. So let's see. So let's say maybe I change it to 5. Okay, so first I go back to the x. Okay, so what's next? And then I run this. Okay, I get some value. Now I'm going to compute my old value over 22. Now let's say what's the new value? Okay, value is okay 18. Oh, now it's better. So that means what? What is this value? This value is 0.15 times. It's saying that, okay, if you move like this, maybe it's too little. Maybe you can be more greedy, move more. Then if you move more in this figure, it's like you move like here. Then of course you go further. Okay, so that's a basic idea. Okay, this is very basic idea. Of course, these are just simple stuff to illustrate. Now I'm going to talk about how we automate this. First, we are not going to type this line by line. Come on, nobody do that. So now I'm going to say, first of all, comment this, and comment this. So we don't care, okay? And then I will run all this, okay? And then what? Usually you name computer cost value at xi9. So of course this is the same thing. So I will call it fi9, okay? Function value at initial point, and then I comment it. I don't want to show it. And then I have an initial x, x equal i9, okay? This should be the initial x, okay? Then what I'm going to do? This is like what? Starting x. So I assign x as my starting x. Now I don't do this. Now I will put everything inside for loop, okay? For loop, do you see that for? If there's a for, that means I need an n, okay? And then what I'm going to do? Let's say I run 100 steps. So let's say I call t equal 1 to 100. You can think of t as the time. So time 1, time 2, time 3, time 4. In optimization, usually people use k. Okay, now I just use t. Doesn't matter, okay? And then what does it mean? It means I'm going to repeat this step 100 times. Okay. So if I run this, so let's say I hide this. Let's say I run this. It will be what? It will be a bunch of x 100 times. So it's not good. I'm not going to show them, so I'll hide them. So if I run everything, you see nothing. But how do I get the record of how well this is approaching? So every time when I run this, I will record the value at ft equal to this. And then what? After that, I plot my f. Okay, this is what I do. So this means I start with x, and then what? Okay, to make the code a little bit more readable. So first I will have an alpha that is 0.5, find my gradient like this, and then what? Do my gradient update. And after I finish my gradient update, I compute the function value at step t. T is 1, 2, 3, 4 up to 100. And after the for loop, I will reach here. I will plot my f. So now run this, and this is the curve. So this is like y is the f value, x-axis is the iteration, and this means function value is decreasing. Okay, this looks good, but this curve looks very ugly. To make the plot looks better, first of all, I want to make the line thicker. So line width, I make it 2. So let's see what happens. Now you see the line become thicker. And of course, you can make it line width at 20. Let's see what happens. Super thick, but this is too ugly. Okay, so make it 2. 2 is okay. And without any comment, always by default, MATLAB will plot the curve in blue. Let's say you don't like blue, you like red. Okay, then you do something like this. This means the color is red. This is color code. Now you see it's red. Of course, you can say I have green. Okay, if you put green, then you will be green. Then what about yellow, orange? Okay, what are the code you are available? You check MATLAB online. Okay, probably the red, blue, green, K means black. Okay, because blue and black start with B, so they run out of vector. K means black. And then what's next? Let's say I don't want to plot solid line. I want to plot dot line. So I put colon here. If I do this, then it will change to dot line. But let's say I put 2 hyphen here. It will become broken line. Okay. So these are, again, you can study this. And if I put hyphen and then X here, it means I put some label at each node. So let me zoom it in. So you see at different point, there's a cross here. Okay. And of course, you can change this to what? V, it will change to not a cross, but a V. Okay. So you see now it changed to V. Change to V. Okay. Change to V. And then there also, again, if you put it as, it will change to a square. Okay. Now it's a square. Okay. This may be difficult to see, but anyway. Or if you want to make it more visible, you can say marker size. That means, well, the name suggests marker size. I make it 20. Then run this. Now you see all the squares become very big. And of course, now this becomes ugly. So 20 is too big. So I make it 10. Okay. So now run this. You see, now it looks better. And of course, maybe square is ugly. So I make it X. So square will be useful if you want to plot those bar chart error bar. But now I want to know the X. Okay. Or you can say, I don't want this. I just want a dot. Then you just put a dot. Then now you see it's a dot. Okay. But anyway, I go back to X. So now this is a plot. Then maybe you said, I want the grid line. I don't want n so empty. Then you type grid on. Grid on. Then you just run this. Now you see there's a grid in the background. Okay. And now you say, oh, I want the Y label, X label. There's nothing. Then you just add X label. Okay. You just type something. For example, I type here is X label. Okay. I type here is X label. I just run this. Now you see here is X label. But oh, you said, oh, the font size too small. Then I click font size. I want to make it bigger. So 22. I just run this. Now you see here is X label. Then similarly, you can have here is Y label. Then you make it Y label. Here is Y label. Okay, I run this. Now you see Y label. And of course, we don't call this here as Y label. We call this function value at each iteration. Okay. Then you just type this. Now you run this line. See, now we get something like this. Of course, you don't care if you don't call it X label. Here is X label. So you call, let's say, iteration T. Now you run the whole thing. Now it's iteration T. And maybe sometimes you want to write an equation here, $sign here. Okay. And then if I do this, let's see what happens. The T will have $2 But in this case, it does not know what does it mean. So you need to add something called interpreter. So this is telling the MATLAB should read this as a LaTeX. So if I do this, let's see what happens. Now you see this T is a math mode. And I can also change this function value each iteration, right? So I can just say, why not just f x t? Okay. I change this to f x t. Now this is in math, so I need to add the interpreter. Okay. So I have this, and then let me run everything again. Now you see f x t, iteration t. And lastly, with the X label, Y label, why not add a title? So title. Okay. And of course, I can say f x t versus iteration T. Okay, then I just add this. I just run everything here. Now you see I have title. Okay, so and then this is a very typical graph. And very typically, you are going to compare this method with other methods. So let's say I run another method. So everything here is like a method. So let's say now I run another method. Okay, so in that case, you will call your x f some number. Let's say I call it f0. F0 means the guy being compared. This is just my notation. And then other people comparing, I will call it F1, F2, F3. So now I have another F. This is F0, this is F1. And let's say for this F, I use a bigger step size. Instead of 05, now I use 08. Then what's next? I'm going to plot the 2F. So I have F1. I don't want to mix up their color. So this one, I will plot it in magenta. So, and then I will do something called hold on. Hold on means I don't overflow the figure. I will allow them to plot on each side by side. So now I'm going to run this. So let's say run this. Now you see I have two curves. The original one is the black one, and the new one is the orange, the magenta one. And of course, by looking at this figure, it tells you what? Well, the orange one is better. No, the magenta one is better because the magenta one uses a bigger number. Then okay, right now please don't worry about what is the best number over here later. But this is to show you, this is what you typically will do. You will plot a curve that looks like this. It tells you how fast it converges. And in this case, the black one is better than the black one is worse than the magenta one. And then if you want to observe what's happening here, you just click this magnifying glass and then go to here. And then now you see, you can zoom in. Okay, so that means what? In iteration 80, black one have an error this amount. Magenta has an error this amount. Okay, simple. Okay, and now let's go back to the plot. Let's go more advanced. This is a plot. What? plotting the f. But what if I want to see the difference better? So here is the thing. First, I will introduce the idea of subplot. Subplot means you plot more than one. So 2, 1, 1. What does it mean? It means 2 row, 1 column, the first figure. So let's say I do this. Let's say I do this. Now you see it's squeezed because it's saying that I will have 2 row, 1 column. This is the first one. Then I'm going to plot the second guy here. So that's exactly what I'm going to do. 2 row, first column, second guy. And now if I just do this, it will just plot the same figure here. But now I want to change something. Instead of plotting this, I'm now going to plot this curve in log scale. So I'm going to semi-log y. Okay, this is in log scale. That means what? Y is in log scale. So let's say I run this. Okay, in this case, you see nothing. Well, because this figure on the original plot, in terms of log scale, is in 1 unit because this basically is the same thing. So that means it's not very useful. But if I do the following, I now do the following. I call it something called f mean. What's f mean? F mean means the smallest value in all the curve. So I'm going to make a f mean and then mean of what? The smallest value, right? It will be mean of f1 and then mean of f0 or f1, f0, f1. And then I put it in a vector. This means I'm going to have a mean of f0 as my first guy and mean of f1 as my second guy. Then this is a vector. I will put this vector inside another mean. It will give me the 0.317 thing. Okay, so let me run this. So you see 0.3174. Okay, then what's next? I'm going to, in this plot, I will subtract this f0 and f1 by this f mean. That means I subtract them by the f mean. This is now telling me how far each of the f converts to the best obtained value, not in the absolute f scale, but in a relative scale. So in this case, I have to change my y-axis. So I will not call y label f this. I will call just f min. Okay. Now I will also change my title to minus f min. So now let's run the whole thing. First, I run this f min. Now I will run the second part. Okay. Something is. Let me try to see this. Okay. So what's f min? Okay, f min. Okay, in this example, f min 0.3174. You can look at this curve. If I minus all this value by this extremely small number, it just shifts the y-axis this little amount. Therefore, you cannot see any difference. And also, I make a mistake here. There should be a minus sign. Okay. And also now you see this is f min. But if I want the min in the subscript, I can do this subscript and then put a brace bracket and then hex. Let me try. Is it working? Okay, it is wrong. So maybe text RM. Okay, it's working. So it's text RM. So I need to use a text RM. This is LaTeX, basically just LaTeX. Okay. Okay, let me run this again. Okay, now okay, I got this. Good. Okay, now this is just basically the illustration. And then let's say, oh, I forgot what is black and what is magenta. Then you add something called legend. Legend, just add legend, right? Legend. Okay, legend. And then let's say I call this method one, and then I call this method 2. Let's see what happens. Okay, now I'm going to run all thing. Okay, so now you see I have this method 1, method 2. Oh, this is too small, cannot see. Okay, first I will define this as LGD. I have an object called LGD that stands for legend, and then legend dot font size. I make it bigger, 20. Then let's run the whole thing. Now you see it's bigger. Okay, maybe I can make it even bigger, 25. Okay, now I make it bigger. Okay, now you see I make it bigger. So method 1, of course, you can name your method 1 by something. Let's say I call it GD, and then let's say method 2 I call it GD2. Okay, then I run the whole thing again. I get it. Okay, so you now got this. Okay, so now let's say I'm going to do a new experiment. So I'm going to clean everything. Okay, let's say I make the problem size bigger. So let's say I make a 10 variable and then 100 variable here. So now I will run this. Now I have something. Now, okay, so now go back to this. I can make this a little bit better in the code. If you look at this for loop here, this guy always compute inside the for loop. That's stupid. You shouldn't compute something that repeat itself in the for loop. So what should you do? Put it outside for loop. So I will put this A transpose A outside. I will call it ATA, and then let's name this here. And then what is this? This is A transpose B. I will call it ATB, and then put it here. And now I can replace all this ATA by just ATA, and same here. And this will be ATB. Okay, this is ATB. Okay, now I got this. Then this will be a little bit faster. And if I run this thing with this alpha, that means I don't need to define it here, right? So I can also take it out. So make the constant thing outside the loop will improve efficiency. Okay, what's next? Well, let's say now go back to the theory. Okay, I actually talked about it last week. What's alpha? Alpha has a way you can compute it. This is what I talked about last week. So what's alpha? Alpha can be a value called 1 over L. What's L? L is the 2 norm of A transpose A. Okay, so I'm going to have an A transpose A 2 norm. Okay, what is 2 norm? The largest singular value of A, or the largest eigenvalue of A transpose A square root. Okay, or you don't want to deal with this, you just call MATLAB to calculate them for you. L is what? Norm ATA 2. Okay, then it will give me some number. You see, L is this number. Then alpha is 1 over L. So I will, let's say this alpha is 1 over L. Okay, then now I have a constant alpha for all the things. And then now let's say for this particular guy, I use this 0.08. So now I'm going to run whole thing, and I get something like this. Now you see something different. First of all, if you look at this graph, in the very beginning, they look very similar. But now you also see that they quickly converge to some value that you can't tell which one is better. This is the reason why you have the plot in the bottom. Because if you make a zoom here, well, you need to zoom so many times until 10 to the negative 5. You see that, oh, black one is actually worse than the magenta. You need to so many times zooming. But you see, what does it mean? It means this difference only show in log scale. Then why don't you plot them in log scale? That's why I have this semi-log y. It's like saying that instead of plotting this in linear scale, I plot them in log scale. Okay. And then you may also wonder, okay, can I make all this label bigger? These are too small. Maybe you can't see in the screen. Yes, we can. So if I want to do that, I can add this line called set GCA. Okay, and then font size 220. Get current figure, and then let's say I put this in my code. Let's say I run this. Now you see this become bigger. Okay. Okay, so now everything become bigger. Okay, so again, this comes from here. You do this, and now let me go further. So I can actually make this whole thing as a function. So now I'm going to make this whole thing. I don't want to type this. I want to make it a function. So now I'm going to make a function. So how do you do that? I make a new code, and okay, here I'm going to save this. I'm call it main. Okay, I'm going to save this and call it main. Okay, main. Now I have a file main. Now I'm going to save the whole thing like this as a function. So I delete them and go to a new script. I call function. This means I'm going to have function and always have this. This is practice, means end of function. Okay, and then you have to type your function name. So let's say GD. That means gradient descent. And then you put a bracket. The bracket means what is the thing inside needed for this function. Well, because you need this thing, so you need what? You need A. So I put A here. And then what? You need B. So I put B here. And what? You also need XINI. So I have XINI here. And then you also need what? Okay, it seems it's everything. Then done. So what's the output? The output is if you just make a function like this, it won't do anything. It will just run this and without telling you what is the output, because you don't specify what's the output. So you actually need to type something called output here. So I'm going to type what output? The F value. So I will call this my F and will get F. So this F will be this F. That means after running all these steps, I will get my F. And usually you have more than one output, right? So you put a bracket, means you have more than one output. I will also have some input, let's say a num-iter. That means how many iteration. And then I will replace this by the 100. Then I can control how many iteration I do. Okay. Then I will have this. And then I also want to know what the X looks like. So I have X. Then I have this. Okay. Then I have everything ready. Then I save. It will call GD. Okay. I call it GD. Now I'm going to copy this whole thing here and replace here. So I will have A, I have B, I have X, I, number of iter is 100. Then I call this and I call this F0 and my X0. And I'll just run this. Okay. So do I have F0? Yes. Do I have X0? Yes. Can I get this back? Yes. You see, I get this back. So now I have squeezed this chunk of code into just one line by writing a script. So I'm going to replace this by something else. Okay. So now this is gradient descent. So that means what? I run this, and then of course you can make function within function. Let's say I make I don't know how to compute gradient, so I'm going to make a function called get grade. Okay, get grade. Okay, I make a function called get grade. And what is the get grade? I just need to do this. So I have a ATA X and B. So I will get a grade F. Then what? This line. Okay, this is ATB. So I will have to put ATB here. So this line, I can replace this line by this line. So this is actually a little bit looks like programming. So sometimes if the expression here is very simple, then you don't need to make this function. This is stupid to do that. But it's possible that the math here, the expression is very complicated. Then instead of writing a very long expression that I told you can go to over the screen, you make a small function and you call it, and you put all the complication inside a function. This is easier to debug. Okay, this is a programming perspective. Okay,